aragonite, at least one variety of aragonite. And I'll pull up some other pictures. That next to it, right there, that clear thing is calcite. They have the same chemical formula. CaCO3. You always thought of caves? Yes, sure. Now, you can find aragonite in caves. It actually can be stalactitic or like a stalactite. Calcite is the clear mineral in that image. Aragonite are the brownish red looking ones. They're this color. They're typically colorless or clear. Aragonite is, or white. But this actually has a color because there's usually sediment or some kind of mud that's trapped in there, giving it that kind of hue to it. But if you look at some of the minerals on the edges, you can see some of them actually do look clear. And I've even seen samples of this where half of it looks kind of brown and the other half actually looks white. And it looks really, really pretty. And I would like to have some other samples like that. So aragonite, again, is a polymorph, which means it has the same chemical formula of calcite in this case, which is CaCO3. The interesting, cool thing about this, though, is that at about, I think it was 400 degrees Celsius, after that, aragonite actually alters to calcite. It doesn't like to be aragonite at high temperatures. So apparently calcite is more stable at higher temperatures, but aragonite is more stable at higher pressures. And in fact, because of this, not because of this solely, but it can occur in metamorphic rocks, which I didn't know. I actually did not know that until I started researching this more in detail. I mean, it will effervesce do you want me to drop some hydrochloric acid on it, drop air? It will absolutely effervesce. That is one of the distinguishing properties of carbonates. Calcite and aragonite included. You drop a little bit of, in my case, dilute HCl or hydrochloric acid. It will react and break up the mineral such that you see little bubbles until, well, the reaction is gone because there's no more HCl to use up. So it effervesces and it makes little bubbles. I love minerals, all the minerals. This mineral can be found all over the world. The particular samples that I have, I believe, are from Morocco, but literally, I have a list of all the locations you can find them, and I will read them off to you. I'm just going to recap. We're looking at the mineral aragonite. It is the brownish red-looking mineral here on the screen. It is a polymorph of calcite, which means that it has the same chemical formula. Calcite is also on the screen. It is the clear mineral, which is trigonal. The other is orthorhombic in its crystal system, which means that is how the structure of the mineral is formed. Not how, but it is the structure that it takes when it forms. And that is all due to chemical bonds, the atoms in the minerals, all sorts of different chemistry properties, right? And I'm going to get into that because there are certain cations that actually replace calcium and make different minerals. Aragonite has two planes of cleavage, but they're both kind of indistinguished or imperfect. They're not great. They're not amazing. However, calcite has three almost perfect planes of cleavage. So if you were to gently tap this calcite mineral, in fact, I really, really want to, it should theoretically break along those cleavage planes, because what a cleavage plane means is that it's weak on the atomic level because of specific types of bonds that just happen to be weaker in a specific direction. Now, certain minerals can be called what's isotropic, and that means they're the same in every direction, and then they wouldn't have, in that case, any cleavage planes. And so here's another thing that's really cool. Although this beautiful little piece of calcite, this clear mineral here, has three planes of cleavage, you can actually have up to four. One of the most common minerals that has four planes of cleavage is fluorite. Now, I'm not going to destroy any of my fluorite to show you. This piece of optical calcite is actually man-made, and I'm happy to destroy it. Oops. See? It actually created some dust right there because this mineral is like, I think, a 2.5 to 3 in hardness. I don't think it's very hard. I think you could almost scratch it with your nail. No, I think it's just about 3, maybe 3.5. I can't quite remember off the top of my head. I don't know which one I want to break. Not that one. Is this the one that I dropped? Maybe the one that I dropped would be good. But it's got some nice... No, that one's got some cool inclusions. I like that one as is. That's fine. All right. And you can also tell it's man-made because it has actually stickers on it that say made in Brazil. So to be considered a mineral, it actually does have to be inorganic. And it can't be man-made. It has to be naturally occurring. So technically that calcite, although it is a mineral because it's man-made, it's not. All right, now I've got my rock hammer. We're going to smash this because I want to see if I can actually show a cleavage plane. I'm really hoping this works. I might need to put it on something hard, actually. Hold on. It does not want to break. There. Perfect cleavage planes. You're going to see this. You're going to see this. This is so cool. Look it. So it made even a tinier rhomb. And another tiny rhomb. And another, well, this is actually part of the bigger piece that those came off of. But they broke into the exact same shapes. They broke into the exact same shapes because of the cleavage planes. So there. Proof that I'm not crazy. And then there's all these other tinier ones too. Technically, though, this mineral is triclinic. So this is calcite. This is not aragonite. This is all calcite. Now I'm going to have to clean this up. That's fine. I'll clean it up later. All right. This is the aragonite that we're looking at. It's very vitreous, which means it's shiny. These are all pieces of aragonite. Again, vitreous because that's how the light reflects, absorbs, or transmits, right? Through or off of the mineral. And in this case, there's an index of refraction of about 1.5 to 1.7. I rounded up. And this means that it has not quite an adamantine, or I'm sorry, it's vitreous, but not adamantine and shininess. Because if you remember, the index of refraction actually has to do with how we quantify its shininess. And we do. So what we do is we divide the speed of light through a vacuum by the speed of light through the mineral. And that's our index of refraction. Not adamantium. Oh my God, adamantine. So these also have words that describe this. So in this case, it's vitreous to resinous. Now, typically it depends on, I guess, the professor or whatever, but oftentimes we don't really go too in depth with the refractive index unless you, I guess, are going really, really high into mineralogy. But it directly correlates with its luster. So I personally like to talk about it. Anything over 2 is metallic. Does that make sense? So if you have a refractive index of 2 or higher, it's going to be considered or have a luster that is either maybe submetallic or metallic. We've gone over cleavage. Now hardness is about 3.5 to 4. I think it's slightly harder than calcite. Actually, don't remember calcite's hardness off the top of my head, but we can just Google that. I think it's slightly harder than calcite. I might be wrong. Its streak is white. So is calcite's. They're pretty similar in that way. The colors actually can be pretty variable, but again, it just depends on what it is, the situation in which it grows, what other elements are in the system when it grows, what things did it trap. In the case of this, it's usually a bit of mud that gets trapped in there. So it's actually aragonite that turns into calcite ferrovax typically, and it has to do with its stability at certain conditions. So aragonite is stable at high pressure, low temperature conditions. So after about 400 degrees C, especially if an environment is arid, it'll actually alter into calcite. It'll completely change its structure. Its crystalline structure will change if the temperature is high enough. And I have a little graph to show you about this as well, ferrovax. Does that answer your question? And I've also got a bunch of occurrences of aragonite in various places that they form. And I can tell you about where calcite forms, at least in sedimentary environments. Sediment. Okay, so calcite is very common and can precipitate in sedimentary environments very, very easily, very, very quickly at very low temperatures. But you need pore water with those chemicals, those ions floating around in it. You need all of the right stuff or ingredients to make that mineral. And those ingredients are pretty common, so it's not going to be that hard to find in a sedimentary system. Prismatic, acicular are just two types of habit that it can have, but there are actually quite a few more. I've got some notes that I'm going to go over with you guys. It can look a variety of ways. This is just one way, and this is actually called Sputnik, Moroccan Sputnik, I think. I think that's how they call it. I want to actually look that up to make sure, because I read that in one of the textbooks that I have, and I never got the chance. I ran out of time to try to Google it to see. But this, if you Google Aragonite, this is typically the image that comes up. These rounded these rounded and twinned brownish red minerals, right? And by twin, I mean that they have multiple crystals growing out from the same place at different directions. So they're literally twins of the same thing, right? That's why it's called twinning. And we call it that. And there are a variety of different types of twins depending on the mineral. But in this case, they're just everywhere. They're in almost a spheroid shape, right? Diaphaneity just has to do with how much the light actually goes through it. Can you see through it or not? Is it transparent or is it opaque? In this case, it's transparent to translucent. I don't know that there are any strictly opaque varieties. I haven't seen any. It's brittle. So this kind of ties into the hardness. How hard is this thing? Well, this doesn't take into account its tenacity. When we talk about geologic things being hard in terms of minerals, we actually kind of split it up. There's hardness and there's tenacity. Whereas in material sciences, it's toughness. And I think it combines both of those things. But in this case, the hardness is 3.5 to 4, but its tenacity is brittle. So it's going to break very, very easily. If you drop it, it hits something just right on that spot and it just shatters. Just like quartz. Quartz is brittle too. A lot of minerals are brittle, very brittle. But not all of them. They can be sectile, they can be ductile, they can be plastic. They can deform in all sorts of ways, depending on the pressure or the stress that you put on that thing. They can even be piezoelectric or pyroelectric, where you put pressure on something and it starts to vibrate and make electricity. They use those things in minerals, in technology, like watches and clocks, or it's the same thing, but you get my drift. Minerals are cool. Not only do they make up all of the rocks on our planet, but we actually use them all of the time, all of the different minerals, all the time for different commercial uses, which is why mining is a thing. All right, we talked about it being a carbonate. There's all sorts of different chemical systems that these minerals are part of, and this one is a carbonate, and you can tell because it has CO2 in it. This is CoCO3, but that means there is CO2 in it. It can occur in sedimentary and metamorphic environments. I'm going to elaborate on this. It doesn't have a lot of commercial uses, unfortunately. It basically has the same commercial uses as calcite, but it's not as abundant, so it doesn't really get used like that. As for jewelry or gems, it doesn't often get faceted. You can get minerals that are gem quality, but it's a relatively brittle and soft mineral. I wouldn't want it as a piece of jewelry. That and it's anything acidic, slightly acidic, can help weather it very, very quickly and easily. So let's say you are working, I don't know, cooking with some vinegar. I actually think that it could affect that. So don't... I wouldn't want a piece of jewelry made out of aragonite, personally. Converts to calcite above 400 degrees C in arid environments. And that is everything I wanted to say from this mineral screen. So I'm going to go back to the other learning screen because it's a bit bigger. I've got a microscope camera here that we can use as well. So some of the other things I wanted to talk about was that, okay, it's a polymorph of calcite. It's relatively unstable. Yeah. Calcite is, yep. Twinning is commonly making the appearance of hex. Oh, that's part of the other thing with this. Some of the twin patterns can actually make this mineral look hexagonally shaped, but it is not. It's indeed orthorhombic. However, it can take columnar, stalactitic, acicular, I think fibrous, radiating, different type patterns. And in fact, I think it even looks somewhat coral-like sometimes. If I remember correctly, there was a sample from my own undergrad that looked a lot like coral. Real shapeless. It was interesting. It can be found near oxidation zones, like a lot of the other minerals we talk about, which is, pretty cool. And it then forms as a secondary mineral due to hydrothermal veins or hydrothermal waters carrying, an abundance of ions and fluids. Of course, the stalactites are going to be in the caves. A lot of these are found in Mexico, specifically, not all of them, but a lot of really good aragonite stalactites are found in some caves in Mexico. I'm hoping we can find some images here in a moment. Coral-like aggregates actually do form in iron ore deposits specifically, so I'm hoping to find some pictures of those. Those are called flos-ferri and mean flowers of iron, which is interesting. Flos-ferri, it's F-L-O-S hyphen F-E-R-R-I, as in ferrous, right? As in iron. It can also form from biologic processes, and a lot of shells. I've actually mentioned to you guys before that CaCO3 makes up shells of a lot of creatures. Well, it's actually the aragonite form, not the calcite form. So a lot of shells from critters are made up of aragonite. And when they die, those things can be buried and can then later become part of the system in sedimentary environments, like I've personally studied, which is really, really cool. So some of the areas or locations you can find like really good quality or abundant amount of aragonite, or including the Czech Republic, Mexico, Morocco, a ton of locations in the U.S., France, Germany, England, Italy, Hungary, Austria, Japan, and I think that's all of them. So if any of you guys live in any of those places and you would like to find some of your own aragonite, you might be able to. And in just a moment, I am going to be showing the microscope version of this. In fact, I could probably talk and show it to you because I've got a bigger one and a smaller one, and the smaller one's crystals are longer, they're more prismatic, they're better formed, better developed, and they're slightly clearer. They don't have as much mud trapped in them, so that reddish hue isn't there as much. Flos-ferri, yeah, it does work. Aragonite was named in 1790 after the Spanish province of Aragon, where it was first noted. Well, so this is one of the pieces of aragonite I want to show you. I'm going to keep one of them over here, too. So, this is one of... Ooh. I bet you could see the orthorhombic shape much, much better because these actually look... It gives you the illusion of those hexagonal shapes. But I think... Oh, wow. That's really, really cool. You can actually see through it quite a bit. Quite a bit better than I was able to before. It's fairly vitreous surface, too. Ooh. Oh, there's a tiny one. There's a little tiny guy. But you can see how some of the twinning patterns, they grow together, and then it kind of makes this... It almost looks kind of hexagonally shaped. It's a tricksy little mineral. It's trying to trick you. Ooh, there's some of it that's actually white. Some without any mud inclusions. Oh, this is a much more resinous luster. It's not quite as shiny. Huh. Interesting. Maybe just that crystal was, because this one's got a pretty... No, they're all pretty resinous. Oh, there's a little pit in there. That's pretty cool. All right, let's see. Layered aragonite is sometimes polished and sold as onyx, I found out. But here's the thing. Onyx is actually a microcrystalline form of quartz, typically. And it's much more durable than aragonite. But it is pretty nonetheless. No, well, if it's a quartz variety, yeah, it is, because the quartz has this hardness of 7, whereas this has a hardness of 3.5. So I mean, aragonite isn't going to hold up as well as quartz. Shells of marine invertebrates are sometimes made of aragonite. I mentioned that. Aragonite sputniks are from Morocco. These are like the ones that I have. There are other forms, long prismatic, flos-ferri, radiating, and cyclic twin, and I want to look up all of these. They can contain trace amounts of strontium, barium, or lead. That's the other thing. So calcium is quite often replaced in this case by strontium, barium, and or lead. Not all the time, but in some cases. And if in enough quantity, they actually form completely different minerals. Witherite, strontianite, and I can't remember the name of the other, but we're going to look at it. I've already got it pulled up. And those, the reason they're replaced by those specific cations or atoms are because they have the exact same charge. So it balances everything happily. So it's a neutral charge when everything bonds together. Oh, wow. Wow. You can see that. You can see the crystal shape there really, really well. You can tell that it's orthorhombic there really, really well. But this mineral here, the twinning has caused this one to look, oops, I lost it. It looked like almost, because it's two, it looks, well, I don't know how many, but a bunch of different minerals probably grew together, and no longer can you see the shape of the crystal system. So it kind of almost tricks you into thinking it's hexagonal. The mineral is replaced by barium. So if you've got the calcium in this mineral, because if you recall, chemical formula for this mineral is CaCO3, calcium carbonate. So if calcium is replaced by barium completely, then you have a new mineral called witherite. I almost actually bought a sample. I'm regretting it. It was very pretty, but kind of more expensive than I was willing to pay. If it's completely replaced by lead, then it's called sericite, I believe. Yeah, sericite. There's another one with a similar name that's in a completely different group, and I keep confusing the two. If it's replaced with strontium, then it's strontianite. Whoa, that name was so creative. So, interestingly, this isn't the only mineral that calcium is replaced for barium and strontium. This happens all the time in feldspars and other minerals because they're very similarly sized. So it's easy for those atoms to swap out for one another if they're in the system together. Additionally, they have the same charge, so it also keeps everything neutral and happy in chemistry. And it's so cool to me.